Okay, as we move into Chapter 2, we're going to discuss polynomial functions. And so in Section 2.3, we're going to talk about a lot of vocabulary and how to graph polynomial functions. That's kind of the end goal for us here in Section 2.3. So I'm not going to read all of these vocabulary words to you word for word. I am going to expect you to read through them yourself and to make sure that you understand what all of these words mean. But I do just want to kind of highlight a couple of them. First of all, here in letter C, a term. Each monomial, meaning each individual item in this polynomial, is called a term. And the leading term right here is the term where the highest exponent belongs. And so whatever that highest exponent, which by the way we call the degree, which is not a vocabulary word on here, but you're going to hear me say the word degree a lot. Whenever I say degree, I mean the highest exponent in the polynomial. We're going to concern ourselves quite often in this section with what the leading term is. And then finally, I want to discuss this theorem just down here at the end. So it says that a polynomial function of degree n, where n is some whole number, some positive integer, has at most n minus 1 local extrema. So remember, extrema means maxes or mins, or you can think of that as being like a turning point in the graph. And a polynomial function of degree n has at most n zeros. And so that means that, for example, if I have a polynomial function of degree 7, then that means that that polynomial can have at most 6 local extrema. It might have less, but it cannot have more than 6. And it's going to have at most 7 zeros. It might have fewer than 7. It might have equal to 7, but it cannot have more than 7. And this is useful whenever we want to try to match up functions with their equations or their graphs. Like if we have the function, we want to be able to match it with its graph. This theorem is helpful in order to do that. Okay, we're going to discuss how to determine the end behavior of a polynomial function here in this nice little table, just to keep you organized here. This is why I put this on your notes. And so let's take a look at this top left box first. We want to try to figure out what's the end behavior of any polynomial that has an even power as its leading term. So, for example, a leading term with x to the second, or x to the fourth, or x to the eighth, or something along those lines, with a positive coefficient. So remember, coefficient means the number in front of the term, and we are talking about the leading term in these cases, in these 4 cases. So let's start with positive coefficient and an even power. Is there a function that you know of that has a positive lead coefficient and an even power? And if you think about it for just a second, hopefully you would say something along the lines of f of x is equal to x squared, and think about what that graph looks like. It looks like a quadratic that opens up. And so it turns out that every polynomial that also has an even degree, or highest exponent, and a positive lead coefficient has the same end behavior as x squared. And that end behavior goes up in both directions. And so I'm going to draw arrows that go up in both directions. And then what happens in between the ends kind of just depends on what the function looks like, as far as, how many terms there are and what the actual degree of it is. And so that's why I just kind of draw a sketch in the middle here. But I know that at the ends, we're going to be going up on the left and up on the right. And so these two end behavior limits are both going to be infinity. And I sort of informally refer to this as up behavior, since it goes up to the left and to the right. Now, what if we have an even power with a negative coefficient? That would, for example, be like f of x is equal to negative x squared, which would be a parabola that opens in the downward direction. And so if you take a look at the end behavior of a graph like that, it is opening down and down. And so it turns out that every polynomial that has an even degree or even highest exponent, meaning 2, 4, 6, 8, 10, etc., that's its highest degree, and it has a negative lead coefficient, it's going to have this same end behavior. What happens in the middle as far as how many turning points there are and how high the graph goes, that all depends on the other terms. But the leading term, that very first term that has the highest degree exponent, that is what determines the end behavior. And so you can see that we would informally refer to this as down-down behavior, and both of these end behavior limits would equal to negative infinity. Now let's take a look at this top right box, which is talking about an odd degree and a positive coefficient. So what function has an odd degree and a positive coefficient? How about y equals x? Do you know what y equals x looks like? That's just the linear function that goes through the origin. And so it turns out, just like with even, every function that has an odd degree and a positive lead coefficient is going to have the same end behavior as that linear function right there. So what happens in the middle kind of just depends on the rest of the terms, but the ends are going to be what I informally refer to as down up. And so what that means is that the limit as x goes to negative infinity of f of x is going to equal to negative infinity, and the limit as x goes to positive infinity, the right end behavior is going to be positive infinity. If I stick a negative coefficient in front of that function, remember from section 1.6, that just reflects the function over the x-axis. And so instead of being down up, it's going to be up and down. And so again, what happens in the middle sort of just depends on the other terms, but we know what's going to happen at the end because of the leading term. And so the limit as x goes to negative infinity of f of x, that would be the left end behavior, that's going to be positive infinity, and the limit as x goes to infinity, that would be the right end of the function f of x, that's going to equal to negative infinity. And so again, one more time, all of this is determined by what the leading term is. And we're going to summarize that on the next page. Okay, so real quick, just to summarize what was in that picture just above, what does the end behavior of a function depend on? It depends on two things. Is the degree even or odd? And so again, what do I mean by degree? I mean highest exponent in the polynomial. So just as an annotation there, when we say degree, we're talking about what the biggest exponent in the entire polynomial is. And if it's written in standard form, meaning descending order, then that leading term is going to be at the very front of the polynomial. And then secondly, it depends on positive or negative. And I'm going to be more specific here. I'm going to say lead coefficient. Okay, so you always want to make sure that you're looking at that leading term, at its coefficient, and at its exponent, and that's going to determine what your end behavior is for the polynomial.